new and innovative methodology for packing a container. Wojciech Matusik is an MIT professor and co-founder of Inkbit. Hello, Wojciech. How are you?
Good. How are you?
Good. Thank you very much for taking the time to speak with me. It's a very interesting methodology that you developed. And I'm wondering if you could just start out by telling me what was the origin of this initiative to understand the optimal 3D placement of objects within a container.
This is a very old problem called a bin packing problem, and this problem is can be found up in many different industries. Uh, an old problem, and we have been looking at it from the perspective of additive manufacturing. In additive manufacturing, you need to print a tray full of material, and you would like to print as many parts in a tray as possible.
Mhm.
So here it's obvious that we wanted to design an algorithm that and a system that would allow you to be able to make machines as productive as possible and pack
Mhm.
containers.
Yeah. Okay. So obviously, you had previous applications of the algorithm to look at the, as you say, the bean packing problem, also the cannonball stacking problem, or the what was lacking in those methods that required something new, a new approach?
So we looked at the efficiency of the packing algorithms, and we examined every single algorithm that is available, and it turned out that they are not very efficient. So that's number one. And second, the algorithms take really, really long time, so they are extremely slow.
Mhm.
So, and in general, they are not going to be very practical because you have to wait hours in order to arrange these objects into a bin, especially if you have lots of objects, hundreds of objects. So that's why this motivated us to create new types of algorithms that would be much more effective compared to other approaches.
Mhm. Now, you talk about it being a way to pack items within a tray for additive manufacturing. Also, some people refer to that as 3D printing. That seems like a fairly small scale application, but does this also apply to larger types of containers, like actual shipping containers and that sort of thing on a wider scale?
Absolutely. Absolutely. Applied. This is a well-known problem applied across many different industries, specifically in the shipping industry. So if you have shipped goods to your house every day, I think you would definitely want to use this, take advantage of this type of new algorithms that we are developing. Similarly, ships, packing objects into large containers that can be shipped overseas. I think you can find applications of this everywhere. Packing containers for trucks that move goods across the countries. Again, another applications. Even potentially packing things that go into the orbit. It could be another sort of
Mm.
application. So I think we can sort of see tons of different applications of this type of technology.
You refer to the methodologies involving dense, interlocking free, and scalable spectral packing. Would you please explain
Yes.
to a layperson what is spectral packing?
Spectral means in frequency domain. So this is a specific algorithm that works in the frequency domain, and this is maybe a mathematical lingo, but any kind of signal can be expressed also in the so-called frequency domain as a compositions of let's say sinusoids with different frequencies. So if you take an image, you can express an image using a set of sinusoids with different frequencies. So you might think, what does this have to do with packing? This doesn't seem like a very obvious connection, but there is a very strong connection between building things or designing algorithms in frequency domains and the so-called convolution algorithms, convolution operators, where you are really have two signals and you want to sort of look at the overlap between two different things. So in this case, this starts to make a little bit more connection. If you have two different things, in this case, a packed container and a new part, then computing this overlap between the container and the part can be done very, very efficiently using this algorithms in the frequency domain or spectral algorithms.
Well, when I hear spectral, I think of the word spectrum, and I think of the ultraviolet to infrared spectrum of radio waves, of light waves, and things like that. But I'm still trying to understand how you apply the word frequency to a physical object, or is you applying it to a digital manifestation of that physical object? Where I don't quite understand how frequency comes into the picture.
Yes, so you can think about it as object. Object is going to be discretized into a set of voxels. If you were to think about it in terms of images, this will be in terms of you would discretize an object into a set of little blocks, and then you have this one object that has one set of blocks. This is the packed container, and then you have another object that's the new part, and you want to kind of see kind of how much they overlap, right? And that overlapping operation can be computed very, very efficiently using using convolution operator, and doing it in the frequency domain makes it very, very fast. And this is the key insight from this
You use
work.
the word voxels. We talk about a container being voxelized. Is that what voxel means? A block, an individual block? What is exactly is a voxel?
Voxel essentially is a discretization of an object into a set of small little cubes. So you take a 3D model and you effectively to change the representation, you discretize it to make an approximation of that object. And so you make an approximation where the object is really composed of tiny blocks in space.
Mm-hmm. Okay, so how does this work? I can understand how it can work in a virtual world, how you could have this representation, and the images that you sent me are actually fascinating, the way that everything just fits so beautifully into everything else, completely compressed and packed perfectly. How practical is this in the real world when you also have to take into account things like weight, like food grade, hazardous materials, things that may or may not, should not go together? I mean, are those elements also thrown into the mix, or are we just talking about this ideal visualization that you then have to modify to relate to a real world packing situation?
So there is one important additional consideration, the so-called interlocking consideration. So the idea here is that when you have two objects, right? For example, I could have one object and the another object of packed like this. They pack very densely, right? But they would be interlocked. So you would, if you print, in this case, print this object, you wouldn't be able to separate these objects in the post process. Or if you had an object like this and you would want to pack this, you wouldn't be able to really pack it because there would be the objects would collide. So being able to resolve these interlocks and having algorithms that are able to resolve these interlocks is very important. Our algorithm is able to make sure that all of these configurations are interlock free. So that's key, that you can sort of both put it together, put the whole container together, and then take the container together apart. So that's important. The second thing that you were referring to is different objective functions. Like, for example, the amount of spacing between the objects or weight distributions. These are relatively simple additional objectives that can be laid on the top of the existing algorithm. So, I would say they are very application specific. So, for example, if you have a truck that delivers all of the packages, you probably want to have the truck to have a relatively balanced weight across this. Or if you want to optimize things for this assembly, you might want to put the pieces that are maybe that need to be delivered to the first customers more in front rather than in the back. So all of these additional considerations are relatively simple additions that you can add to the existing algorithm.
But you do have to adjust the algorithm in order to account for these
and
additional.
Each of the applications is going to be slightly different. So, I imagine that if you want to pack containers for shipping across country. This is going to be even slightly different than packing containers for shipping, door to door, for door to door delivery. I think all of these applications might be slightly different.
Who stands to benefit most in the world of transportation and freight planning from this algorithm going forward? Who will get the most benefit?
I think all of the major players, I would say, that deliver these goods to your houses or across the country or across the seas. I think I would say these are these are the companies that would benefit from this the most. But you can also imagine, packaging companies that have sets of goods that are being packaged today. Uh, to for example collections of items that need to be packed very very tightly for for delivery. For example, imagine that you have a product that has a number of different components. How do you build an enclosure, right, and a shipping container that would have this kind of product, right? So I would say even if you buying a drill, right, with different subcomponents, and you are designing the case for the drill, we can absolutely use this kind of algorithm to package all of the items well.
Wojciech Matusik, I want to thank you so much for sharing with us this innovative approach and methodology to container packing that may very well have a great impact on the efficiency of freight and transportation, and as you say, additive manufacturing as well. Thank you very much for being with me today.
Thank you.